Hi everyone, and welcome to our in-depth guide on enhancing processor performance. In this video, we'll explore the various factors that influence CPU efficiency and how they work together to optimize your computer's capabilities. By the end of this video, you'll be able to recognize the primary factors that impact CPU performance, such as clock speed, core count, and cache memory. She will to understand how pipelining can significantly improve processor efficiency and review the fetch execute cycle and its relationship to machine code and assembly language. The fetch execute cycle is fundamental to CPU operations. It involves several stages: fetching the instruction from memory, decoding it to understand the required action, executing the instruction, and then storing the result. Think of it like following a recipe. The CPU gathers the ingredients, which can be considered the data, interprets the recipe steps, which can be considered the instructions, performs the steps, which can be considered processing, and finally stores the finished dish, which can be considered the output. Assembly language translates these machine code instructions into a format that's easier for humans to read and understand. This cycle is repeated continuously, allowing the CPU to process complex tasks efficiently. Memory in a computer is divided into units called words, which can vary in length: 8, 16, 32, or 64 bits. Each word has a unique address in memory. For example, if a computer has an 8-bit address bus and an 8-bit word length, it can address 256 different memory locations. This means that each unique address points to a specific word in memory, allowing the CPU to access and manipulate data efficiently. The size of these words can affect the amount of data processed at one time. This influences overall performance. The width of the address bus determines how many memory addresses the CPU can access. An 8-bit address bus can address 256 memory locations. Modern computers often have a 32-bit address bus, allowing them to address up to 4 gigabytes of memory. This means a computer with a 32-bit address bus can access significantly more memory than one with an 8-bit address bus, enabling it to handle larger data sets and more complex applications. The address bus width is crucial for applications requiring large amounts of memory, such as databases and high-resolution graphics. The data bus is bidirectional, meaning it can send and receive data. Its width is determined by the number of wires it contains. When the data bus matches the word size, data transfers are more efficient. For example, a 32-bit data bus can transfer a 32-bit word in a single operation, speeding up data transfer. This efficiency is crucial for high-performance computing tasks that require rapid data movement between the CPU and memory. A wider data bus can significantly reduce the time needed to transfer large amounts of data, enhancing overall system performance. Assembly language closely mirrors machine code, with each machine code instruction having an equivalent assembly language instruction. The computer's architecture, including word size and address bus width, determines the instruction format. For example, an instruction to load data into a register might look different depending on the processor's architecture. This close relationship between machine code and assembly language ensures that programmers can write efficient code that takes full advantage of the CPU's capabilities. Understanding the instruction format is essential for optimizing software performance and ensuring compatibility with the hardware. Machine code instructions consist of an opcode and operand. The opcode specifies the operation, while the operand provides the data or memory addresses involved. For example, the machine code instruction C50D might correspond to LDA number 13 in assembly language, meaning load accumulator with value 13. This direct mapping between machine code and assembly language allows for precise control over the CPU's operations. Machine code is the lowest level representation of a program, and understanding it is crucial for debugging and optimizing software. Several key factors influence CPU performance: clock speed, number of cores, and cache memory. Clock speed determines how many instructions per second the CPU can execute. More cores allow for parallel processing of multiple instructions. Cache memory provides fast access to frequently used data. For example, a CPU with a higher clock speed and more cores will generally perform better than one with lower specs. Additionally, larger cache memory can significantly reduce the time it takes for the CPU to access data, further enhancing performance. These factors work together to determine the overall speed and efficiency of the CPU. The system clock generates regular pulses that synchronize CPU operations. Faster clock speeds result in quicker fetch, decode, execute cycles. For instance, a 4 GHz processor ticks 4 billion times per second, meaning it can process more instructions in less time. This high frequency allows the CPU to perform more operations per second, which is critical for tasks that require rapid processing, such as gaming and real-time data analysis. However, higher clock speeds can also generate more heat, requiring efficient cooling solutions to maintain optimal performance. The system clock produces regular on-off signals to coordinate process activities. Actions are typically performed on the rising edge of the clock signal, and each action takes a fixed number of clock cycles to complete. Think of the system clock as a metronome that keeps all parts of the CPU in sync. This synchronization ensures that all components of the CPU work together harmoniously, preventing data corruption and ensuring accurate processing. The system clock's frequency directly impacts the speed at which the CPU can execute instructions. Modern CPUs often have multiple cores, such as dual-core or quad-core processors. Each core can independently execute instructions using its own fetch-execute cycle. More cores can significantly boost performance, especially for multi-threaded applications. For example, a quad-core processor can handle 4 tasks simultaneously, improving multitasking efficiency. Working in parallel in this way is particularly beneficial for applications that can divide their workload across multiple cores, such as video editing and 3D rendering. More cores can also improve the performance of virtual machines and other resource-intensive applications. Parallel processing involves multiple cores working on different parts of a task simultaneously. This approach can greatly enhance performance for tasks that can be divided into smaller subtasks. For instance, in video editing software, one core might handle rendering while another processes effects. This division of labor allows the CPU to complete tasks more quickly and efficiently, making it ideal for complex, resource-intensive applications. Parallel processing can also improve the performance of scientific simulations, data analysis, and other computationally intensive tasks. Cache is a small amount of high-speed memory located on or near the CPU. It stores frequently accessed data and instructions to reduce latency. Level 1 cache is faster but smaller than Level 2 cache. Cache memory acts like a shortcut for the CPU, providing quick access to important data without going to RAM. This proximity to the CPU allows for faster data retrieval, which is crucial for maintaining high performance in demanding applications. Cache memory can significantly reduce the time it takes to access data, improving overall system responsiveness. Level 1 cache is divided into instruction cache and data cache for simultaneous access. Level 2 cache is larger but slightly slower than Level 1 cache. More cache memory reduces the need to fetch data from slower RAM. With more cache memory, a computer can run programs more smoothly by minimizing delays in data retrieval. This layered approach to caching ensures that the most critical data is always readily available to the CPU, enhancing overall system performance. Level 3 cache, if present, is even larger and serves as a shared cache for all cores, further improving data access times. Pipelining improves CPU efficiency by overlapping stages of instruction processing. Multiple instructions are processed simultaneously at different stages of completion. This technique maximizes CPU utilization and throughput. Think of it like an assembly line. While one worker assembles part A, another worker assembles part B. Pipelining works similarly by keeping all parts of the CPU busy. This continuous flow of instructions ensures that the CPU is always working at maximum efficiency, reducing idle time and increasing overall performance. Pipelining can significantly improve the execution speed of programs, especially those with repetitive tasks. To summarize, the main factors affecting CPU performance are clock speed, number of cores, and cache memory size and type. The address bus width determines the maximum RAM size, while the data bus width affects operand size in instructions. Pipelining enhances efficiency by overlapping instruction stages. A high-performance CPU combines fast clock speed, multiple cores, ample cache memory, and efficient pipelining techniques. By understanding these factors, you can better appreciate how modern CPUs achieve their impressive performance levels. This knowledge will also help you make informed decisions when selecting or upgrading your computer hardware. That's the end of this video. Please give it a like or subscribe if you'd like some more. Thanks for watching. Bye for now.